Yeah, so good evening. I apologize for the delay. Good evening. So I welcome you to this problem solving and live interaction session for the subject engineering mechanics. So this is more of a recap session of all the weeks. So I just have some representative problems from all the weeks that we have seen so far, right from the starting of statics to the end of 3D kinematics. And the idea is not to solve the entire problem as we have been doing in the sessions, but just to brief through some of the nuances that are there. And in the process, if there are any questions that come up, that we can address it. In the meantime, if you are having any questions, you please feel free to ask, and we can take it from there. So, okay. So let us look at the first question. So it says the total internal angle at each vertex of a symmetric star is 36 degrees. And it is known that the vertical distance AO is twice the clear perpendicular height of the arm as shown. So the height of one arm is shown. I'm sorry. So the height of one arm is shown to be 3 meters. And then we have been told that the internal angle is 36 degrees and the star is symmetric. So in that case, we can see that half of the angle, which is 18 degrees, in that case, we can see that this will be 18 degrees and this will be 18 degrees as well. Okay, and we have been told that this AO is basically twice this height. So this AO is nothing but 6 meters. So we can see it from there. Okay. So now it says the position vector of vertex B with respect to D is what? So essentially we have the basis here. And why we are trying to find the position vector? Towards the end, we are trying to calculate the moment about vertex D. So what do we know about moment? It is R cross F. So R, or rather I should say moment about D. For this force's contribution, if I have to see, it will be R of B with respect to D crossed with F of B. Similar for the other case. So in this case, I know the force magnitudes already. So all I need to do is to actually take the cross product of this. So now I can see that this force is essentially passing through this point. It is concurrent. It is essentially passing through that point, in which case we know that these two are parallel. So if these two are parallel, the cross product is 0. So this won't be having any moment contribution about D. So in case we don't want to go about solving the long way, we can simply see that this will not be having any contribution, in which case we need not even consider this into the equation. Whereas this will have a contribution, and we know that this is R, this is R of E with respect to D. But this crossed with this will essentially involve only this perpendicular distance, which happens to be 3 meters. In this question, this is given to be 3 meters, while this is perpendicular. If this is perpendicular, then R, if this is R of E with respect to D, then we can see if, let me call this some distance alpha. Okay, so moment about D would be R of E with respect to D crossed with force F at E. Now this cross product will essentially result in Fe R of E with respect to D sine theta, which happens to be 1. So we can see here, if this is theta, we can see that R sine theta is nothing but force E All these are magnitudes, by the way, into alpha. This will be my moment about the magnitude. So I can right away see from the question, when this is given, I know this distance alpha, I know the force F, it is 20. So right away I can write the moment to be 60 Newton meter. As for the position vector, it is just a basic. Yes, yes, please. Any questions? Yeah. Okay, it will come out to be the same actually. Okay, I understand your point. Let this be theta. Now, if you take sine theta, it will give you alpha. Is it clear? Yeah. So, and the basic position vector we can calculate based on this distance. First, we will have to evaluate this distance, which will be equal to this. And what will this be? We can see if this angle is 18. So this distance we can calculate with 3 and 18 degrees. So twice of that distance will be this much. And from here, from this triangle, we can easily calculate its position vector. So a little bit of geometry. So essentially what we need to solve these and problems similar to these are a good grip on sine rule, cosine rule, some rudiments of other trigonometric equations. That is, I should say, force vector resolution and vector composition, which is inverse of resolution. So this, if we are comfortable with these three, then majority of the problems can be solved very easily. So most of the problems only come in the calculations dealing with these, other than the concepts, which we will see as we go about. So I hope that that is clear. Yeah, yeah, yes, 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 yes. Let us say that there are two vectors. This is P, this is Q. Now what we do is we take it here and then we make it like that. Yeah, now what is the question that you're asking? Uh, Actually, one with respect to the other would be this. Yeah, this angle. Hmm. Angle of that relative velocity vector, if they have just said angle, then what they mean is angle with respect to some datum, xy, with respect to x. Otherwise, they have to specify. So let us say that in your example, this is the velocity of the car, and this happens to be the velocity of the train. Now what you are doing is you are putting it like this, and you are joining this magnitude. Let this be m. If this is a, b, then m you can easily calculate. If this angle you know, then m squared is nothing but a squared plus b squared minus 2ab cos. theta. That with that being theta. This is the cosine rule. So from this you can actually get m. Now once you get the magnitude of m, so m by sine theta, let this be alpha, this be beta. So this gives us b by sine alpha is a by sine beta. What are the unknowns here? M is known because just now you have calculated. Theta is known. That is how you actually calculated m. Some constraint must be given. B and A you know. So alpha and beta you can easily calculate. Clubbing, these are three equations, right? So two at a time you can take. These two at one time and these two at a time. Opposite, no? B's opposite angle will be its denominator. Yeah, that the question has to qualify that properly. If that is not qualified properly in the question is ill posed. It is not your fault. Either they must have said if the relative, okay, let us say that they have said you are traveling in the car and then you are observing the train and you see what is the relative velocity vector. That could imply that they mean with respect to the car's velocity, what is the angle that the relative velocity is forming. But such questions need to be coined properly. That is, it should not be ill posed. It should at least with reference to some datum they have to give. Otherwise, there could be. In other cases, what you can do is once you have found alpha, beta, then you can go about identifying using the angle. These are tricks of this thing. But essentially, concept-wise, they have to specify this. Otherwise, it could be interpreted as anything. So at least in our course, we have tried to maintain questions in a way that they are unambiguous. Is it clear? But one thing I would suggest is don't get hung up too much on the semantics of the problem because same question can be posed in different ways. So unless I mean we can only hope that they pose questions unambiguously, but in the case of ambiguity certain compromises have to be made. There is no other go. What you in the context of the question, yes, this interpretation is correct. So we have to look for sources which give us unambiguous questions so that we don't fumble on our fundamentals. That is more important rather than the semantics of the issue. Okay, yeah. Okay. A claw hammer is used to pull out a nail from a box as shown. It is known that the perpendicular force of 100 Newton is required to pull out the nail out of the box in this configuration. Consider the contact surface at A is sufficiently rough to prevent any slipping and answer the following questions. What is the tension in the nail during this pulling out process? What is the magnitude of the force in Newton exerted by the hammer head on the block at point A? And considering the same tension is required to pull out the nail, if the distance AO decreases, the force required to pull out this nail would decrease. So essentially what we are trying to say is it it is acting like a hinge here, and then as soon as we apply this force, it creates a moment. This would actually try to rotate this hammer, but this is prevented by a force. That force is developed due to this friction here, and that nail is what we are trying to pull out. So essentially we have a force like this, which about this point it creates a moment like that, and then we have a force like this about which it creates. Now we have been asked a limiting condition. What is the, let us say that it is known that 100 Newton force is applied. That is, as soon as I apply 100 in this configuration, this will give way, is the idea behind the question. In which case we already know that this is the limiting force. So that limiting force multiplied by this gives us a moment like that, which has to be equated to our 100 Newton multiplied by 150. So when those two moments are equal, this is at the verge of being pulled out, which is what we mean by 100 Newton force is required to pull this out. So by balancing moments, we can do that. Another thing is now the force at this point. Now we can essentially resolve the forces into two components. One is along the length of the hammer, one is across the length. 100 doesn't have any component there. So this we can transfer it here. We know the trick that once we transfer this force here, it will come with a associated moment. And this force can be resolved into two components now. Sigma, considering this to be one direction and this to be another direction, we can do our force equilibrium and find this out. Now the third question, what it is asking is, considering that the tension required is same. So whatever 100 into 150 divided by 50, whatever force we got here, that is the tension required to pull this out. If the distance AO decreases, this is distance AO. This is the distance AO. If this happens to decrease, then the force required would also decrease. So what they are trying to say. Now we know that this tension is causing a moment like that, which needs to be balanced or rather overpowered by a moment applied by the force. Force is R, moment is R cross F. This is R and this is F. So R crossed with F gives us this. So the moment about A due to this pull out force is R of O with respect to A cross F. And this needs to be equated to the moment about A. This is due to force due to 100 Newton, or rather due to F, I should say. Let me call this F. Is also equal to 50. This has to be equated to the uh, moment due to the bolt nail. Sorry, this has to be equated to the moment due to the nail. So now we have been given a constraint that this happens to be same because R is not changing for that, and the force required to the tension that needs to be mobilized is also same. So this happens to be constant. So what we have been asked is there are three quantities where the right hand side is constant. Now in the left hand side, if one decreases, other would have to decrease in order to maintain that equation, which does not hold because this will be a rectangular hyperbola. So as soon as this decreases, this would have to increase in order to mobilize. So if we were to instead hold the hammer here and pull, we would have to apply a higher force. If we were to hold it, we have to apply much higher force. So that is the essence behind this question. So this deals with just the rudiments of how to take moments, how to do equilibrium. So that is what it is. So I suppose that this is clear. Anyway, so we have representative problems from all weeks. So we will once see through and maybe get the questions clarified. So I will not be solving this fully because the solution answer you already know and method I have just explained. So you can go back and work it out once because these are just from the assignments. So let us look at this question from trusses. So a truss is arranged such that each of the smaller triangles is an equilateral triangle. So what do we mean? Each of these is an equilateral triangle. And what do we know about an equilateral triangle? The sides are equal. That is A, B, C. So from our sine law, A by sine alpha is B, A by sine beta and so on. Sine delta. So this where this happens to be A, B, C, or rather all three are A, alpha, beta, delta. Okay, so we know the direction cosines of all the forces essentially. If this is the force, then we know that its component here will be, if this is F, this is 60 degrees, so this will be F cos 60, that will be F sin 60. Similarly, we can resolve for everything. Okay, so let us just calculate the reactions first for this question, just to know how to proceed. So we have this, fine. Now I go here, and then for this entire system, for this system, I draw the free body diagram. I know that this we will treat it as a rigid body. So let me apply. So let me apply the reactions. So this is a hinged end. So it will have two reactions, which will be AY, AX. Call this X. Let this be Y. And this happens to be a roller in the question. This is a roller. So it will offer only vertical restraint. So this will be BY. Now for this entire truss, which is in equilibrium, it is a planar condition. So equilibrium equations, since we have already defined this to be the xy plane, in general, equilibrium entails external equaling 0 and sigma m external equaling 0. This is what static equilibrium demands. In this case, we can see that it will be sigma fx equal to 0, fy, fz. Similarly, if I were to resolve the moments, x sigma my, sigma mz. This sigma mz implies that it is about the z-axis. So, for example, this is x, this is y, z is pointing out of the plane of the paper. So, whatever moments that we calculate on this xy plane will have its axis about z. That is, it will be parallel to z, plus or minus, depending on the cross product. So, this is called the vector equations of equilibrium. These are the scalar components, which means these can be added. That is, if we are doing sigma fx, if we resolve the forces, let us say that there is one force here, which we have resolved like this, and then there is another force here, which we have resolved like this. So these can be treated independently. These can be added independently without any problem. That is what scalar addition is. That is why these are called scalar equations of equilibrium. With that brief, now we are dealing with the xy plane. So in the xy plane, we have sigma fx, sigma fy equaling 0. These are the force equilibrium equations. Because z is not coming into the picture here, we are talking only about the xy plane. Similarly, we can take sigma mz, sigma moment about z equaling 0. This also comes within the in-plane action. Others are out of the plane. Now, globally, in this system, what we have drawn, essentially we have replaced the all the supports with reaction forces. So how many unknown reaction forces are there here? Ax is unknown, Ay is unknown, By is unknown. So there are three unknown forces. And we have three equations of equilibrium at our disposal to find these unknowns. Each and every equation, as many number of unknowns are there, as many so many number of equations you need in order to find. If it is less or more, it will be a problem. So there are three equations, three unknowns, so we can systematically apply this. So we can see that sigma fx equaling 0, if we add ax, is there any other horizontal force on the system? There isn't. So trivially it gets satisfied. It tells us that ax is equal to 0. Not trivially, easily it is satisfied. Trivially means something else. These are trivially satisfied. 0 equaling 0. Okay. So sigma fx equal to 0 we have used up, ax we have found out. Sigma fy equaling 0 will give us summation of all the forces along y. So what does that give us? Ay plus by, y plus, because this is pointing in the positive y direction. Similarly, 20 and 10 would be negative. So it will be minus 30 equaling 0, or this would be equal to 30. So this gives us another equation. The first equation gave us ax is equal to 0. Now we can take moment about any point in order to find our unknowns. So there could be a question where to take the moment. If we are having two unknowns, and if we can find a point where where the contribution of either one of the unknowns goes to 0, then that equation will directly give us the other unknown. For example, if I take the moment here about ay does not contribute there. Ax is already 0. So when I write the moment here, it will have only one unknown in the form of by. One unknown, one equation, so I can directly get that. So that way I can calculate by, substitute it back, and I can calculate ay also. Having done that, I have satisfied the equilibrium globally, and I have come to know what the unknown reactions are. So from this moment on, I will start calculating the member forces. So what is asked? What is the magnitude of net reaction at A at B is asked, that we can see, that we have seen how to find that out. Now let us consider this. Force in member EH. Which is EH? This is EH. So how do we go about solving this is one question. Now one approach is, let us take this joint. At this joint, I'll just elaborate this a little bit, because this is a stress also happens to be a scoring topic in the exam. So if at all you have any doubts, it is better that it gets addressed now, so that at least you can easily get this right in the final exam, those who are taking the final exam. One is the method of sections, the method of joints. Let us say that I isolate a joint like this, using that circle, using this cut. I cut this and I take what is on the right side. So what will I see on the right side? I have one force like this, which is 10 kilonewton that is applied. And then I have two members, and then their forces. This is another member and its force. Now this we have seen that we represent forces pointing away from the joint and consider those to be representing tensile forces. So whenever we isolate a joint, the general convention is we will point the force away from it. So we have isolated this joint I. So we have actually put all the forces pointing away from it. Now, if the answer comes out to be positive, it implies that our assumed direction is correct. And this assumed direction, using the sign convention, implies that the member is in tension. So there are two steps to it. Don't confuse it with the fact that if you are getting a positive answer, it has to be tension. Both are D-linked. If you are getting a positive answer, it implies that the direction you have assumed is correct. And since you have started with the condition that the direction you have assumed represents tension, that is why positive implies tension in this case. Okay, so this is force Fi, this is force in member Hi, and this is joint I. So at this joint, now I know that the entire system is in equilibrium. So any subsystem that I cut, it also must be in equilibrium, because small part, it's a part to whole concept. So this also has to be in equilibrium. Now in order to analyze this, I again can apply these three conditions. I can see that these two are concurrent force. All the three forces are passing through this joint I. So if I take moment, it will be 0 equal to 0. So it will not help. So at each and every joint, I have only two useful equations that I can use. Hence, I should only cut joints where there are only two unknowns. If let us say I start by cutting this joint. If I started by cutting this joint, I'll be able to see that I will expose 4 unknowns. But I have only 2 equations with me to solve. So it will not give me a answer right away. That is why say the method of joints, we should systematically start applying from a joint where there are only two members connected. So that way, stepwise, if we go, once we solve this sigma fx equal to 0, sigma fi equal to 0, we will get these two quantities, positive or negative, depending on what it is. So if we have marked this as from here at this cut, if we have marked it like this, it implies at this end it will be like that. If both are pointing in the same direction, it will have rigid body motion. It is undergoing tension or compression. It is only that when I push the right side this way and then I stop it, it is only then the member is getting tension or compression, depending on what I am applying. So whatever I apply here at the opposite end of the member, I should apply the opposite way. I hope that is clear. So in such a case, once I find these two quantities out, systematically I have to do this at every joint in order to find out. So in the question, if it is asking for force in EH, which is this member, then I have to first solve this joint. Then these two are known. Then I have to solve this joint where this is known and these two were unknowns. Now these two also will be known. Then I have to go for this joint where these two are known, these two were unknown. Now those also are known, out of which one happens to be EH. We can clearly see that it is very time consuming. At the same time, this is a simple configuration. If we had a truss which is say 100 meters long and we have been asked some member force in between, we cannot solve it using the method of joints because it is impractical. It will take forever to solve. So what is another way to do it is the method of sections, which I will discuss now. Let us say that I take this portion alone. Now similarly, as I have seen that when the truss is in equilibrium, a joint has to be in equilibrium. If the joint has to be in equilibrium, any subsystem I take should be in equilibrium. Let us say I have taken a section like this. So this exposes one force, this exposes another force, and this exposes another force based on this. And wherever this intersects, this is actually which joint it is, joint E. Now we take only this side. To this system, can I see that this system is not a concurrent force system? Because I have two forces that are parallel, two forces that are perpendicular to those two parallel forces. This is not a concurrent force system. So what is the benefit of that? In addition to sigma fx equaling 0, sigma mz equaling 0 also will give me a viable answer. So these three can be applied at this section. Now it is easy to see that method of joints is nothing but a subset of method of sections where we isolate only one joint. If I just, instead of cutting it here, if I were to cut it here, it becomes method of sections. So it is one in the same. Just that the joint happens to be concurrent, so it is a little more time consuming. Now from here, I can label these forces. This is force in H, H and G, H and E, E and F. So this is force Fe. I'll remove this. Actually, this is not part of our problem. And then this will be H. This was Hg, which is He. Okay. So now we have at least come closer to having our force that is required readily available. Now what about moment about which point if we take will these give us quicker results? Let us say that we take moment about this joint E where it was intersecting. So when we take moment about this, we can see that these two contributions will go to 0. So in one shot, we can find out what is sigma, what is FHG. This will have a moment like that contribution, and these two forces will have moment about that E. So that we can quickly sum up and find this out. Once we find this out, can we see that vertical equilibrium has to be satisfied? In this case, if I do sigma Fy equal to 0, let us say, what does that give me? I have one component force like this. This force is Fhe cos 30. Because the entire thing is 60, so this is 30 degrees. So Fhe cos 30 I get. Are there any other vertical forces? These two are vertical forces which are known. So just by taking this section and doing sigma Fy equal to 0, I can find out Fhe at once. So like this, if you practice several problems, you will be able to see, to get a force in one member, how to take moment or force equilibrium, so that you can reduce your mathematical steps in the process. So similar to this, I would encourage that you might have already done, because this is the assignment question. So how to take moments, which points to take moments, or how to add up the sum to reduce your I'm not necessarily saying that it will get solved by one equation. It just that it will be easier if you work that way. So any questions? Yes. Yes. If this, I'm sorry, if this equilibrium equation is violated, satisfied. Okay. Okay. Yeah. Yes. Yes. No, stability, you have to check the arrangement. Statically determine it. Yeah. So M plus R equaling 2J. First of all, in a plane, why do we do this? Why it is M plus R equal to 2J? I think we already discussed this during the live session also, but I'll just reiterate. See, why do we add M? Because we know that once we have idealized this as a truss, the member can have only one force, one magnitude of force. It can be tension or compression, that depending on the sign, that's fine. But essentially, it is carrying only one unknown. So if we add up the total number of members, it gives us the total number of unknowns that are there. Going outright solving a problem like this, I don't know, first of all, what are the reactions that are getting mobilized. Secondly, I don't know what are the forces developed in these members, which is actually carrying higher force and which is carrying lower force. So all these are unknowns. So the reaction forces are three. So R happens to be the external constraints that are provided, which happens to be 3 in this case. Total number of forces, member forces. If I add up the total number of members, gives you the member forces. So the sum of these two, so essentially M plus R equal to 2J, the left side sums up all the unknowns in the problem. The right side, we saw it's a concurrent force system. So at each and every joint, I have at best two equilibrium equations that will give me viable answers. That is why this gives us, at each joint, it gives me two equations, these two equations. So if I have one joint, it will give me two. As many number of joints are there, multiply, double those many, I can get equations. So that is why we equate this. But this does this carry any information about the arrangement? I may well have arrangements that are such that this gets satisfied. But when you analyze subsystems, like we did for this, it will not be in equilibrium. For example, let us say this force was not there. Let us say this member itself was not there. That is, I am talking about a condition where in the absence of this member. And let me connect some other member like that. Let me put a through member which connects joints E and joint C and G. In this case also this will get satisfied. This m plus r equal to 2j will get satisfied in that case also. But after removing that, if I were to cut the section, this is what I will be seeing. I hope you agree. This is what I will be seeing as the free body diagram. In which case, if I do sigma Fy equal to 0, what does the left side give me? 0, because there is no force to balance that. 0 equals minus 20 minus 10. These two forces we have to add up. So this is not holding, which implies that this is not holding, which means acceleration is not 0. So there will be some movement. You are not making that uh, maintain static equilibrium, which is why arrangement has to be checked specially over and above m plus r equaling 2j or 3j as the case may be. So that arrangement has to do with stability. This is a mere requirement. If this itself is not satisfied, then naturally it will not be a truss. So if this is satisfied, then we have to go ahead to the next step and check the arrangement. If everything goes well, then we can say that it is stable. Yes. Yeah. For simple cases, for simple trusses that we are dealing with in this course, if it is following triangles, it will most likely be stable. The thing is, if we go for complex cases where I showed a truss where connections are like these, and then if we go to 3D truss, then it will become more involved. But for the purpose of this thing, you can consider that if you look at triangles and they are forming neat shapes, then there is no problem. And there is a reason behind that. See, if you take two members, let us say I connect two members like these, both of these can rotate about this. They are having some rotation. Now let us say I bring in a third member and connect these two, something like that. If I were to connect these two, now the movement is totally arrested. Movement, relative movement. Anyway, one would have to be grounded. That is a different thing. But I'm saying the relative movement gets arrested. So a triangle happens to be the simplest uh, case of a truss. Now, if I add two more links, I form another triangle which is in equilibrium with reference to this. I add another one. This is rigid now because it is not having any movement. So like that, if you see only triangular shapes that are built up, this is the reason why it will most likely be stable. So I hope that that is clear. Yes, it could be. Over constraint means you have provided, if I put a, instead of a roller, let us say I don't allow it to roll, then this becomes over constraint. Over constraint meaning whatever is the bare necessity to keep this in equilibrium, over and above that I am providing some support conditions. Are these needed? Yes, these are needed. Does this have any effect on the forces? Yes, that will also have. If I have all these free expansion allowed, then if I heat the system, let us say, if I heat the truss, then this is free to expand. There will be no forces developed in the members. Whereas if I have an over constrained system, now if I heat it, because of the heat also, the members will experience some force. So that also needs to be added. These are anyway matters of uh, higher level courses, but this is what an over constraint system is. Yeah. Okay. Are there any other questions? And mind you, I can also explain it in Hindi or Tamil. These are the two languages that I know. So if there is a need, because this happens to be the last session, if those some any one of you is taking the exam, and if you need me, if there is a language issue and you need me to explain in Hindi, that I can do. So I hope that you have understood that. Okay, so with that, let us see beams. Beams also happens to be a very scoring topic for the exams. So I would suggest trusses and beams you do well, practice well. Needless to say, other topics also you should practice well. But these are easily you can grasp, is what I'm trying to say. Okay, so this question, what does it ask? We have a beam, a simply supported beam is given. We have been asked the reaction at A, reaction at B. Then which of the following is correct? Something about the shear force diagram and bending moment diagram. What is the shear force equation? What is the bending moment equation? What is the maximum shear force experienced? So let me just briefly show this. I will not go into much detail here. Let us say that we take the beam initially. So the first step is to calculate the reactions. To calculate the reactions, what is it that we do? We will replace the joints, the supports by reactive forces depending on what kind of supports they are. We saw at this end it was a hinge, so we will have two supports. Essentially, I will have AY and then I'll have some AX. Similarly, I'll have BY here. And for the sake of completeness, I always try to do it by first principles by marking everything. But as you go about solving, you need to pick up speed. So just by seeing it, you should be, that is, you can take that as a metric. Just by seeing the beam, if you are able to gauge which reaction will be more and quickly gauge the magnitudes and draw the shear force bending moment diagram, then it would be helpful. So sigma Fy equaling 0 gives me AY plus BY equaling, what are the forces that I need to add? Minus 3, minus 3 into this distance, which is 1. So this will be minus 3 into 1. Are there any other forces? There are no other forces. These are couples. We should not add them in force equilibrium. They do not play a role there. Similarly, sigma m. Now again I can take it about any point. Let us say that I take it about D. I will see that By will have a contribution, Ay will also have a contribution. So again I will get one equation with two unknowns. Here also I have one equation with two unknowns. I can solve for both. But that is not quicker. If I want to do it quickly, I can take moment about this point or this point, thereby eliminating one of either. So which we have already seen in the case of trusses, so I won't delve much into that. Now let us go ahead with, let us say for this configuration that AY and BY is this way, that is pointing upward. AX is not existing, so I will just remove that. Okay, so in such a case, now let us draw the shear force and bending moment diagram quickly. This is one point, this is one point, and then I have it here. Okay. Now I know that if I take a section here and isolate it, what is it that I will get? If I isolate this section, I will get a portion of the beam like that. If I let us say I take a section like that, I'll get a portion of the beam which has AY applied. I don't know why it is not coming. Yeah, so I have AY applied here. and then this is the section which I have taken. There is no other force. Do I need to put any force there? Yes, I have actually cut a section, and I can see that the normal to this section is outward, which happens to be coinciding with the positive axis, which means this is a positive surface. So with looking at the sign convention, the positive surface means just look at what is on the right side and just put them here. I can see this is on the right side. I know this is a positive surface. I have put this here. Same goes for this. That is all I need to do. This is V. This is V. This is M. Now I need to analyze the equilibrium. If I analyze its equilibrium, what does this give me? V is equal to AY, it gives me. So when I go for this sign convention, when I go start from here and my X increases like that, I can see that all upward forces I need to add, all downward forces I need to subtract. That is all that I need to do when I move from left to right, when my origin is also moving, and this happens to be the sign convention. So in this case, I draw a line which represents shear equal to 0. This is my shear force sign convention. I put that here. I put that here. I'll also put the axis for the sake of completeness. This is my axis. When this is my axis and this is my sign convention, when X is moving the positive direction, all I need to do is add up. So in this place, I know that AY is pointing upward, the reaction. So it goes up like that. Then there is no change till I come to this point where I can see that there is a force that is acting in a downward direction. So I need to go down here. How much down should I cross this or not will depend on the magnitude of AY that you have calculated, which you would initially. So I'm just taking that AY is greater than 3. In which case it won't go all the way, it will just stop here. We will just stop here somewhere. I think I can use another color. Okay, it's fine. Yeah, I think now it is better. So from here, it again continues without any change till this point. At this point, there is a moment applied, but we are adding up shear forces. So it will not make any change to that. So I again continue this way. I go till point D. Again, I can see that there is a moment applied, but no force. This force is placed here actually because I resized it, so it disappeared. Again, I continue till this point. And now the key is I have a uniformly distributed load. How does a uniformly distributed load behave? Let us say that I take some section here. So whatever force is in that portion will get subtracted. And how do I calculate that force? This is essentially the pressure intensity. So the area of this gives me force. What is the area of this diagram? The height of this diagram is given to be 3. The width is given to be 1. So what is the area? 3 into 1. It is a rectangle. Similarly, if you have a uniformly varying load like this, how do you calculate the area? What is the maximum B? What is H? Half into BH, triangle's area. That is the total force. That is what this diagram indicates. So if I take a section like this is the force that I need to subtract. If my section is here, let us say, there is no force that I need to subtract, and it is linearly varying. That is, if I were to write the shear force equation, the contribution of this I have at some x. Let us say this is x. and then this is 3, 4, 5. 3, 5. Okay, so this distance will actually be x minus 5. So what is the area of this? It is 3 into x minus 5. That is all I need to do. That is what will appear in my shear force equation. So I can see that power of x is 1, which means it is linearly varying. So at this point there will be no change. And then since that is pointing downward, it will gradually take me down in a line till I reach the end. At the end, I can see that there is again By which has to be accounted for, so I will go up. So this is my qualitative shear force diagram. Why it is qualitative? Because I have not found out Ay and By, whereas when you will solve, you will be doing it. I'm just telling you once you solve for one reaction, how to quickly draw the rest. So I hope that that is clear. Yeah, yeah, yes. At any point that is x less than even 1.4999 will not fall on 1.5. It is told that at 1.5 we have been there is a 3 kilonewton load applied. These are abstractions. In real life, if you apply, it will have some finite area. But with rigid body idealization, we go for point force is also concentrated force is also an idealization. So in this context, what we mean is if I just take a section to the left of this, let me call this section something. Let me call this point F. Just to the left of F, my shear force does not have 3 kilonewtons contribution. Just to the right, it has. At F, it is actually indeterminate. We don't know at F what is the. It cannot be defined. Is it clear? What is the question that you had? Yes, you can see that there is an abrupt jump, no? So we can say generally function should not have jumps. If we have a function which suddenly shows a jump like that, vertical jump, that means it is multi-valued. So at this x, what do I say as the shear force value? I cannot determine a unique value, so it is indeterminate. So we just leave it by joining these 2 points. That's all. Yes, you can fix this left support as the origin. Easier, yes. Why easier? We let us just see. In that case, you can start from a direction where the triangle originates. That is, if let us say this is my triangle, it is not difficult in the sense it will be easier because area of a triangle you readily know. Area of a trapezium is a little involved. So let us say that this is my x, case 1. So when I isolate this, let me also draw the beam actually. Let my beam be like that. Let this be the beam. So at this x, when I take a section from here, if this is W and this is L, can I say what this will be? It will be W by L into X because it's a linear variation. Is there any doubt in how we got this? I hope that is clear. If there is, you please do ask. Yeah, so this is the way it has been applied. Now, if I take sigma Fy equaling 0, it will give me, let us say there is some reaction here, R. So it will give me R minus area x into Wx by L. equaling 0. Whereas if I take from the other, let me take this x dash. So sigma Fy equaling 0 at x dash. So it will be, there will be some other reaction. That reaction will be r dash. So it will be r dash minus, then we will have to go for Wx by L plus W by 2 into x dash. And then it will have V. Sorry, this also has to have V. It will be minus V equaling 0. So this will have plus V. So this is why it becomes a little messy. Other than that, it is straightforward. Overhanging beam. Okay, let us say it is like that. It is overhanging now. What is the question? Oh, okay. So your question is with related to this way. If it is overhanging like that. No, then in that case, what you can do is see, you are essentially adding up forces. So if there is a force here, let us say, and then there is some load applied like this. For this portion, you take x from here. Start from here and come till here. You plot whatever you have got. Now these forces, just apply them as equivalent forces and couples at this point and go about doing your analysis with taking this as the origin. Then it will be simpler. Yeah. If this is my beam, let us say, and then I have a UDL applied here. This UDL is W, let this be A. Now whatever couples and moments I have been applied, something, it is just going on. Now what I want to do is to plot the shear force diagram. Now I can see that this will have a negative shear force. So it will go something like that. For this portion, I can isolate, take x starting from here, and then I can at least get to this point. Once I have done, I will replace this system with another one. I replace this system. After reaching the reaction, I will no longer use this, but I will put a force like that, which will be WA, which is the area. And then I'll have a couple like that, which will be WA squared by 2. Then I can forget about this. I can go about doing my analysis like that. Yeah, into equivalent force and couples. Actually, that is what you do. We are past the stage where we draw free body diagrams and do it. Just looking at the question quickly, if we calculate shear forces and moments at some key sections, the idea is just to join points where it shows a jump. There is an abrupt jump here. Similarly, in the bending moment diagram, there will be abrupt jumps here. So to the left of that point, to the right of that point, if you calculate, you can just connect it. That is all we need to do. So we have seen the brief on beams. So let us see this question. Two links of mass m are connected and constrained as shown. A massless rod DEF is connected to the links at E. This is the massless rod connected through E through a collar and F using a linear spring. This spring DE or spring constant K something. With the application of a horizontal force like that, the angle between the links, so these are the two links, so this is the angle between that, increases, thereby compressing the spring. It is known that the spring's uncompressed position is when theta equal to 0. Or answer the above questions based on this blah 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 whatever is there, and then only a portion of this thing is shown. If this was shown like this. Actually, it will be like that, and then the wheel would be here. Now, when the wheel is here, how will the arrangement look? So I have the pin like that. I will have the member like this. So this is member B, A. Over and above that, I have the wheel here, this roller here. So to the roller, we have BC attached. So there will be another. I'm just drawing. They are identical, it is said, but I'm just drawing it with a different width so that it becomes clear. This is like this. So when this thing closes, what do we see? Here there is a collar. So this rod is free to move through that collar. So this F and E, it coincides at this point. F and E coincide. If F coincides, then I have the rod like that. And this spring, what are its ends? One end is connected to E, one end is connected to D. This happens to be D, and E is over here. As we have just seen, E and F coincide. So the spring is like this. The spring cannot go beyond this point, whereas the rod can go through the collar. So when we pull this apart, the spring is getting compressed. I hope this configuration is clear. Rest is just simple. Once we understand this configuration, to write what is happening, now let us say that the wheel was here, and now it will open up. At some theta, this is the arrangement. So we can see the actual length of the spring is this much. The actual length of the spring is equal to the length of DEF. The massless rod DEF, its length is the actual uncompressed length of the spring. So now at any configuration, this is the actual length, let us say S. S is the unstretched length. Let this be some S in this configuration, SC. So from here we can see that S is equal to SC plus EF. One will come from geometry. So EF will come from geometry. So what we know that these two links are equal. So I have this as the angle bisector, in which case this happens to be theta by 2. So B in this triangle, B sine theta by 2 into 2. This is B sine theta by 2. I have to add it twice. That is EF. In which case, can I calculate what is the net compression in the spring? Net compression is S minus SC. SC is the current length, S is the original length. So S minus SC is the compression in the spring, which is equal to EF, which happens to be B sine theta by 2. Once you get the compression in the spring, can you write the potential energy in the spring? It is half kx square, where x is your compression. So similar to that, we can go about solving this. Now when this is straight, there is one more aspect to keep in mind, that this won't be at the same level. These two are not at the same level. Because this is the point, this is the B is the distance where this is where that collar is provided. Now if I were to draw a circular arc, when it is straight, B will come actually here. So I can see that if B is the center of mass, it has moved through this distance. I hope you are able to see that. So this is nothing but B. 1 minute, let me draw it this way. This is the circular arc of radius B. At this point, when B is vertical, when the thing is totally uncompressed, this is where my mass point is. Now at any stretch, the mass point has moved here. So this difference will be the movement of the mass point, which is h in your mgh based on the datum. So from there you can also write the gravitational potential energy. Then you apply the energy principle in order to obtain the equilibrium of the system. What does the energy principle state? It is just a rewording of the principle of virtual work, which says that the virtual work done by all the external active forces on a system is zero. Not external active forces, all the active forces on a system is zero. So actually solving it by force, I will get one force here, 2 mg will be there because two weights are there, and then 1 kx, the force in the spring. These are the active forces in the system. Now, if I want to solve it by energy approach, I just replace my work done contribution by the mass with the negative of the change in gravitational potential energy. Similarly, if I were to analyze the spring, instead of the spring force, I will recast it as spring potential energy, and it will come out to be the same. Spring potential energy, what we have to do is spring potential energy is half kx squared, and then this is V elastic. So dVe by the degree of freedom will give us, this is spring potential energy. This is change in the spring potential energy will be 2 kx by 2, which is kx, which is again the force. So since these are conservative systems, we have recast all the forces as some potential energy, and we are solving it by that approach. This becomes easier in certain class of problems. That is why we are doing it. But nonetheless, one should practice how to do it by force method, by energy method, and get the fundamentals clear. Any questions on this? Is it clear? Okay, okay. We take it that it is clear then. So the key point or note here is we should be able to idealize we should be able to visualize the displacements, how the system is behaving. Even in case of stability of trusses as you had asked, in all these cases we should feel the structure, how it will behave when we give it some movement, because otherwise we are just doing mathematics. Idea behind this engineering course is that we feel the structure, how it will move, how these things come about, which will also make it interesting. So in that light, I hope that that is clear. Okay, so this is just a small problem from friction. A massless rigid link AB. So we have AB as a link is hinged to a uniform wheel of mass something at point B and to the floor. If the coefficient of friction between the wheel and the floor is given to be something, a couple is applied to the wheel such that motion is impending at this point. Then we have to calculate certain things. Now in kinetics also, we saw that when we have a link which is only applied with forces at the ends, then this link can at best only carry an axial force. And we saw one proof for that. For example, I first of all I consider that let this be theta, and let this still remain hinged. Okay, let that still remain hinged, and let this be the force F that is coming onto this at point B. In this case, let this be some beta. This is not parallel. I shouldn't have drawn it parallel. What I imply to say is, what I intended to say is, force is in some generic direction. Let this be some beta. Let this be beta. Now if this is the force, then force along one force along the member is along the link, it is F cos beta. I am just resolving this into two components. One is along this, which is this F cos beta. Another is perpendicular to this, which is F sin beta. Okay, and this is F cos beta. Now let me take moment about some point. I am free to take moment about any point. Now that I have already replaced this force with its components, this should no longer be part of the system. So I have removed that since I have resolved this into two components. Now I am free to take moment about any point. Let me take moment about A. Let me take moment about A. And this is in equilibrium, so I equate it to 0. So what does that give me? I can clearly see that the force that is passing through the axis does not contribute. Only this would have to contribute. So let this length be L. Let the length of the member be L. So can I see that the moment will be nothing but the moment will be the product of these two, given that there will be no given that it is 90 degrees here. So this is F sin beta L, or rather I should write FL sin beta equal to 0. This has to hold because I can see that it is in equilibrium. So for this to hold, what has to go to 0? I can see this has to hold. Therefore, since F and L are not non-zero, because there is a force that this member will carry, and L is a physical dimension which is non-zero, so therefore sin beta must go to 0, which implies that beta is 0. So this is a proof that if you have a link which is applied with two forces, the force that is mobilized in that link is invariably axial. So yes, this is a true force member. Once this is a two force member, I know that this is axial, in which case it is simple for me to just replace this with its I can simply put its free body diagram quickly, because this I know at what angle this is acting. This is along the axis of the member. So, and then here I have a force like this. So since the moment is applied this way, the nature of motion is towards the right. So the force will have to get mobilized. Friction force will get mobilized in this direction in order to stop this. So that is how we go about solving this. And then same drill, sigma fx equal to 0, sigma fy equal to 0. So because there are two rigid bodies, so we can apply it twice. So for one rigid body, we have already applied it and we have got this. For the other rigid body, once we draw the free body diagram, we can apply that and get it. So I hope that that is clear. Any questions? Yeah. Other end is hinged. Yeah. No, this member is indeed hinged. You are saying that if this was not hinged, okay, let it be. Let there be horizontal and vertical components. These two components will have to mobilize such that the resultant force is passing through the axis of the member. That is how these reactions will get mobilized. Okay. Direction of the member, that is the key here. Yeah. Okay, so let us look at this question. We have just come till it's already 1.5 hours and we have just reached friction. So the other parts, anyway, we will not be solving the questions. So I'll just brief through how to go about approaching the problem in dynamics. So in case of any questions, you are always free to ask. So here, how to identify the friction direction. So let us quickly draw this and also draw the belt or brake band or whatever it is. So we isolate these two. Now there is some tension acting here. There is some tension acting here. We have been told that this tension is P in this portion. Now we just need to see what the nature of movement is and we can easily identify what is the direction of friction. So we can see that in this question, actually this is a brake band. I have not given the question statement. Nonetheless, it can be implied that this disk is actually rotating in this way and there is a brake band that is there to stop this motion. So if the disk is rotating this way, when this belt touches this disk will apply a force like that. A friction, by virtue of friction, it will apply force like that on the brake band. I'm sorry, just a moment. My earphone battery got low. I just wish to take one moment off, please. I'm sorry about that. Yes. So this is how we actually identify the direction of friction. In belt friction and this driven pulley brake band questions, it is just a matter of identifying the friction direction and to see whether the mass of the belt is negligible or not, and we can easily get the quantities. So with that, let us move on to the next question, which has to do with some projectile. So two balls are thrown simultaneously with initial velocities u2 and u1 along from the two floors of a lighthouse, and some constraint is given. So h2 by h1 is 2. So basically this is twice that height, and we have to ignore air resistance and other things. So now it says how many times longer will ball 2 take to reach the ground is what is asked as compared to ball 1. So first, if this is short, we can see that as soon as this is short, this is a projectile in free fall. So it follows a parabolic path from this thing. Now depending on how this is short, this reaches at some point. Now what is important to idealize here is the key point is that horizontal and vertical motion is independent. So these two are independent. What does this mean? So we have the equations of motion. Now mind you, these equations of motion are valid only for a constant acceleration case. In case of free fall, what is the acceleration that is acting? That is acceleration due to gravity, which is for all our practical purposes we are taking that to be constant. In which case we can apply these equations of motion which can be derived in first principles. I also suppose I have done that in one of the sessions, so you can just take a look there. So what are those? So the same this thing we remember, which is the final velocity is as 2a s, and then v is u plus at, and then s is ut plus half at squared. In this case, we will take our coordinate axis. This coordinate axis is pointing like this, so it will basically be plus gt squared by 2. So acceleration is plus g.
So this is for the vertical direction. Vertical. Horizontal, we can again apply this also. I should replace with 2gs, and this also I should replace with plus gt. For horizontal, acceleration is 0. So that since the acceleration is 0, there is no change in the velocity essentially. Final is equal to initial, which remains constant, which means that once this is shot with a horizontal velocity u1, for the entire trajectory it follows, its horizontal velocity is invariably u1. If that horizontal velocity is u1 and there is no difference, then we can, since the acceleration is 0 and the horizontal velocity is u1, we can easily see what is the distance that it will traverse and how much time it will take for it to reach the ground. So that way we can calculate the time taken for this and the time taken for this independently. Then comes the next question, that if u2 is 7, if this is some quantity, based on this constraint, uh, the velocity of ball 1, what should be the velocity of ball 1 such that both the points both hit the same point. So what does that mean? How to interpret that? This has been shot with some velocity and it reached that point, and this has also been shot with some velocity and it reached the same point. What will be common between these two is the distance that has been traveled. So s will be common for these two. u1 is given, u2 we will have to calculate based on these equations of motion. The second one says that let the height be 3 meters. If this is 3, if this is 3, naturally the greater one is 6. And if ball 2 is released, just released, that is from here, with u2 0, it is just released like that. Now it is important to consider this, that in the case of free fall, when it was shot horizontally, the horizontal velocity was not entering our equations of motion, which were meant for vertical motion, since horizontal and vertical are independent. In which case, this was 0. U was not existing. So we can see that S is nothing but gt squared. What this implies is, if I take a ball and shoot it with a horizontal velocity 3 times u2 or 5 times u2, or simply drop it without any velocity, both will reach the ground at the same time. So it is independent of the path that is traversed. The time taken will be the same. So this will reach the ground at t seconds. This will also reach the ground. Only thing is, it will be reaching at this point, but that will also take t seconds. It will take the same time, no time lag. Based on that, it can be easily equated in order to get this. So this is not much of a challenge. Just that the essence behind this question is for the learners to understand that horizontal motions can be dealt with independently. And in the case of projectile, horizontal velocity doesn't change, and there is no acceleration. And in the case of projectile, again vertical motion has only one acceleration, which happens to be the gravitational pull. So okay, so let us look at this. This is a question from absolute motion. So as soon as we see things like these, we should be able to gauge that there are some shapes forming and we need to relate these quantities. So immediately our sine rule and cosine rule, there is a high probability that these can be employed here. Yes, please go ahead. Yes, yes, sorry, I'm sorry about that. Yeah. Yes. Velocity, yes. Yeah. Yes. That is why it mentions that it was released. If it was given a velocity, that is what I mean to say is if this is thrown down, and and you mean the second case also it is having a velocity that is equal, is it? Yes. Drop it. Just release it. Yes. 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 But yeah, yeah. If we impart a velocity while instead of dropping it, if we throw it, then we are imparting a velocity. Then we cannot equate both because this is not zero. Yeah. 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 Yes. Yes. That is what it is. Moving up. How do you know it is moving up? You know it by observing the velocity. You don't know by observing the acceleration. Accelerations we are not observing, right? So moving up or down, it has no bearing on the acceleration. It could be moving up, but the could but slowing down. It could be moving down but speeding up. So it is important to de-link acceleration from the motion. The rate of motion is acceleration, but the direction of motion has nothing to do with acceleration. So that way, if you say that it is moving up and you take acceleration to be negative, you are actually implying that it is moving up but slowing down as it goes about. So you can take negative A. Yes, acceleration's direction we have to consider. Motion's direction and acceleration's direction need not be the same because that depends on the rate of change of that motion, not on the motion itself. Yeah. Yes, please go ahead. Yeah. Yeah. Yes. Yeah. Yes. Yeah. Okay. What was it? Okay. Yeah. So this is traveling with you. Let us say this is T naught, T1, T2 is again traveling with you. This ball is also traveling with you. At this point, what is the distance it would have traversed? This distance would be u T1 minus T naught. Let me take T naught to be 0 for ease. So this will be ut1. Similarly, with respect to the initial position, Now it would have at time t2 it would have traveled ut2. Same goes for the person also. So essentially we have a vector like that, and then a vector whose horizontal component is equal, always equal. So here these were the two vectors: vector of the ball, velocity vector of the ball, velocity vector of the airplane. Next what happened is, this was the velocity vector of the ball, and the velocity vector happened to be like that. Why it increased in length? Because horizontal still remains the same, but gravity has imparted some vertical velocity. That is why the magnitude of this arrow has increased. The length of this arrow is increased. It is, this component is still the same, but now an additional vector is getting added by the by the action of gravity. That is why its length has changed. In the third case, again this remains same. Now this would go like that. It would have gone further down and it would have become bigger, something like that. So in all the three cases, if I calculate the relative velocity, these are the velocity of the plane, velocity of the ball. In all these three cases, if I were to calculate the relative velocity, for relative velocity, what is it that we do? We basically sit on one vector, look at the other, put tip to tail. Now, if I were to put it here and negate it, then I will be able to see that the velocity is actually 0. What I mean to say is there are two vectors. So how to go about calculating its resultant is, put uh, one's tail to the another tip and then connect the opposite ends. So that is how we do vector addition. In this case, if I connect these two, if I connect this like that, it ends up at 0. So essentially, I will be, since I am also moving at that speed, I won't be observing any relative velocity. In the next case, let us say, in this case, what I do is, my relative velocity and Vp will actually make up this. Okay, what I'm trying to say is, there is something that needs to be added to my velocity when I'm observing this. So something gets added and it makes up this vector. That something is invariably vertical, because that is the only velocity that has been imparted. So what is it that the observer in the airplane sees is the relative velocity, which always happens to be vertical. So what that person will see is that the ball is falling along a straight path. What was the question? Actually, I'll try to do some justice explaining that instead. Oh, it is some formula based this thing, is it? There is some something not matching up. Okay, because I don't readily have that. Is it okay if you can? Yeah, yeah, yes, please go ahead. You can post it in the forum and right away I'll try to answer it, because I don't readily have the numbers with me. So yeah, yeah, you can just post it there and I'll. I suppose you have been asking other questions also, which have been answered. Yeah. Yes, please go ahead. You had some other question. Yeah, yeah, go ahead. Okay, of what? Okay, Relative to the hoop. Ah, okay, I understood that question, which one it is. Yes, relative to the hoop, the acceleration, but hoop itself is having some movement, some rotation, right? So in that case, okay, so this was the question. Let us say this was the object. Now when you sit on that loop and rotate with it, what you are observing is that it is having an acceleration like that. It is speeding up like that. Now we can see that this is actually moving along a curve. So at the next instant, along with this acceleration which is changing its magnitude, there has to be some acceleration which has to change its velocity along this hoop, which means there has to be a centripetal component as well. So if the person rotating with the hoop observes the acceleration to be speeding up like this, that accounts only for the tangential acceleration of this object. In addition to this, there will be a normal acceleration pointing towards the center of this curve. This curve. This curve center is here. So there will be a centripetal acceleration like that and a normal acceleration which is responsible for speeding this object up. These two components make up a vector which is ARL, which comes into your RFR equation, rotating frame of reference equation. Now what is the question? See, ARL, for example, if there is a straight member, or why don't I go there? Let us say that you are rotating with this member. We are rotating with this member. What is it that we'll observe? Now when this is rotating like that, we will observe that this would seem to go away from us at some speed. Now that speed could be increasing or decreasing. At some next instant, where will that speed be? Where will that velocity be? Velocity invariably has to be along this path only, right? So essentially, what can at best change in this velocity is only magnitude. The path cannot change. When you are rotating with the member, you can only see the object going along that slot. If the slot is straight, then the velocity that is imparted to this can at best only be along the slot because it is only responsible for the magnitude change of that velocity of that relative velocity. In this case, whatever velocity you measure, whatever acceleration you measure happens to be ARL itself. So if you say that you are observing this peg or pin B, point B while rotating with this member and you observe that it is moving with some velocity VRL and after some time you have again made the measurement and you have deduced that it is actually increasing its velocity. That means ARL is positive and along this direction only. That is one. Now if let us say it was a curved path instead. If this was a curved path, in that case, there are two accelerations at play. One is actually changing its magnitude, which is the tangential acceleration. There is another acceleration brought about by the curve, which is enforcing that point to move along that curve. So the net relative acceleration that that object will experience is ARL. That is what we need to take into account. So for members which have slots or members which don't straight away show the problem as slots but rather some kind of constrained motion like that hoop question, you need to identify what is the path that the object is taking. Is it a straight path or a curved path? If there is a curved path, invariably there has to be normal and tangential acceleration. If it is a straight path, at best velocity only can change in magnitude, not in direction. So ARL will have only one component along the path, along the slot. Is it clear? Yeah, yeah. Okay. Okay, so this is done. So we were seeing this. Uh, I'll just wrap it up in five minutes so that it becomes. Then we can have some discussion if need be, and then we can close. So in this problem, we have been given that this is alpha, and we have been given this distance is d. This d is actually changing by virtue of this coming closer. So if we have to evaluate, we can quickly see that this is a case of absolute motion where this thing can be related like this by this triangle. So I have a triangle like that. If I take this triangle here, this gives me L, this gives me D, and this gives me some other quantity. Call it L. What else do I know? I know this angle is alpha. In which case I know this angle to be pi minus alpha because that's a straight line. Similarly, this is given to be beta. So this I can see it is 180 minus alpha minus beta. So this happens to be alpha minus beta. Now it is just a matter of applying cos rule and sine rule in order to find out whatever is asked. If it is asked what is the angular acceleration of this with respect to a fixed datum, we know it is beta. So beta dot is asked, beta double dot is asked. So once we write the constraint equation, absolute motion question is solved. We just need to systematically take the derivatives and double derivatives. One thing to note here, as opposed to our relative motion questions, where we see that if omega is this way, it is positive, it is negative, if it is this way, it is positive, according to the right-handed coordinate system. In absolute motion analysis, we should not make that analogy. In absolute motion analysis, let us say we have taken this to be beta. If beta dot is greater than 0, this implies that beta is increasing. That is, at some next point, it will be like that, beta plus delta beta. So that is how we should relate. In this question, when we take d dot, I see that actually this is moving in this direction, which happens to be the positive x. But this quantity d is actually decreasing. So d dot will be equal to minus v, not plus v. So that way we should relate in the case of absolute motion analysis. As soon as we go to relative motion, naturally we are going by vector analysis and not by magnitudes alone. Here we are only dealing with magnitudes. In vector analysis, automatically these cross products will take care of the signs. So that is something I just needed to remark. Coincident point analysis we have seen. This also I explained now. So one aspect to keep in mind is ARL is along the slot for straight slots or components resembling slots. ARL will also impart direction change to VREL in curved slots. So only these need to be kept in mind. Otherwise, the analysis is very systematic. You follow the equations, the big equations that are there, substitute for each and every value, and you should be able to do this. Okay, so one thing to note here is that where do we fix the axis? So we generally fix the axis to the slotted arm. Why is this the slotted arm? Because by virtue of this collar or this thing, this crank is actually making this move. So the crank is driving this. That is why this will resemble the slotted arm in this case. We can recast it as a different equation where this is a slot and this moves inside that. So whether it is over it or inside it, that doesn't matter. Which component is driving the other is what we should see, and then fix our rotating frame of reference appropriately. it is not absolutely necessary that our rotating frame of reference should be perpendicular to this or parallel to this slot. It will be easier, but it is not very much necessary. I may well have an axis like this, which again rotates with this member, but it will be a little more involved to uh, visualize that. That is why we generally prefer taking our axis, one of the axis parallel to the member, and the other will naturally become perpendicular. Other than that, it is same. So why do we do this? We want to know everything about this slot, everything about the motion of this slot. What do we know? We know everything about this point. We know its acceleration, we know its velocity. How do we know that? Because this is connected to this crank whose motion is defined. So from the question we see which component's motion is defined. The crank's motion is defined. So any point on the crank, you can actually calculate the absolute velocity. Now we will look at the same point from a rotating frame. Regardless of which frame you look from, velocity has to be objective. Velocity has to be same. By virtue of exploiting that condition, we try to relate that velocity to the angular motion of this slot, thereby calculating the slot's angular velocity, angular acceleration, and so on. That is the basic idea behind rotating frame of reference analysis. Then we moved on to kinetics, where we basically whatever kinematical quantities we found, we were trying to relate it to kinetics. So there are some key, I would say, there are some pointers that are beneficial. Generally, what we do is we draw the body as soon as we identify the nature of its motion. Let us say that it is having a rightward acceleration. So we will mark mg, we will mark some force F, we will mark some other force that is driving it, F1, and then we will mark the acceleration here, A, and then we will add up sigma F in the x direction is equal to mass of this object into A bar. So this is how we generally do, but in kinetics problems it is advisable to draw these two separately. One comes from the free body diagram. One is you draw the free body diagram, and then correspondingly with respect to whatever motion it is having, there will be a kinetic diagram for this. Kinetic diagram will have kinetic quantities, namely m a bar and I alpha. So this is the equivalence of the force, this is the equivalent of the torque. Basically these are nothing but the time rate of change of linear and angular momentum. So that is what this is. This is the time rate of change of linear momentum. This is the time rate of change of angular momentum. I know angular momentum is I omega. So the time rate of change of this is I alpha. So if we write it this way separately, there will be no confusion as to which one should add up where. So in this respect, first key point is we identify the nature of the motion. We have solved umpteen number of problems to identify nature of the motion. How do we do that? We identify any 2 points on the body whose velocities are known. We compare those two velocities. If those happen to be equal and if they happen to be congruent, then it is likely the case of translation. There won't be any rotation. Now again, if time passes, if it happens that the velocities are actually tracing a path, tracing a curve, it is curvilinear translation. Otherwise, it is rectilinear translation. So for those, the rotational analog, namely Ig alpha, there is no time rate of change of angular momentum. So Ig alpha will be 0 because alpha will be 0. Likewise, if there is fixed axis rotation, then naturally there will be no translation but only rotation. So the kinetic quantities that exist will only be Ig alpha. If it is not if it is not rotating about its mass center. If it is rotating about some other point, naturally you can link it through circular motion. We will just see that. So the idea is identify the nature of the motion, draw the free body diagram and kinetic diagram separately, balance the forces out, balance the moments out, and you will get your answers. So for example, if it is rectilinear translation, if this happens to be the mass center, Generally, all our kinematical quantities, acceleration, velocity, forces, whatever we have seen, we have the habit of resolving them into two components, x and y. Similar to that, we will resolve the kinetic time rate of change of linear momentum into two components, agx bar, agy bar, with this as the mass center. So whatever this would have to be affected by some force here. So that force we just equate it to this, write the force equilibrium and be done with it. If it is not rectilinear but curvilinear translation, that curve itself will tell you which is tangential, which is normal. As we did for one problem in kinetics where we saw a plate was moving, so we could identify the axis by placing the axis parallel and normal to that curve. In the case of fixed axis rotation, this is a special case of fixed axis rotation where it is rotating about its mass center. So it has only Ig alpha. Whereas if it were rotating about this point, then this mg bar would also come. This a bar will get related to this alpha by our circular motion equations. Alpha cross r is equal to uh, acceleration a. In the most general case of general plane motion, we will see that we need to identify all the three components, write its force analog and moments analog, add these up, equate it to this in the y direction, add these up in the x, equate it to that in the x direction. Take moment about any point, take moment about the center, only Ig alpha will come. Take moment about some other point, Ig alpha will come in addition to the contributions of this about that point. Only these things we need to keep in mind. Other than that, kinetics is very straightforward. So you can solve a number of problems, and if you have any questions, you can post them in the forum. So anyway, this I'll just leave it aside. Yeah, this is one aspect I just wanted to discuss quickly as to how to identify uh, the which angular velocity is actually changing. So first we take the fixed frame. Fixed frame is the ground. How the question will be posed, there will be components mounted over each other, and then it will be having some complex motion. So in the fixed frame, this platform is mounted, and this platform is actually known to be rotating with this omega. So that platform is rotating. Over that platform we have a barrel, a cannon barrel that is mounted. Now that barrel is being raised, that is at the next moment on the sitting on the platform, at the next moment we will be seeing that the barrel will be here, then it will be here, then it will be here by virtue of this. So inside the rotating frame, we are actually observing the barrel move. What does that mean? Inside the rotating frame, we are observing VREL. So Coriolis force also needs to be accounted for. There will be Coriolis component. Now, the point to be considered here is we are not paying attention to the barrel as such. We are paying attention to this cannonball, which itself is having a relative velocity with respect to the barrel. Let us say we were sitting on the barrel. We will see that this ball is accelerating outward with some velocity as given in that question. Now we sit on this frame and look at the barrel. The barrel also is moving. So in addition to a velocity along the barrel, the ball will also have a velocity like that by virtue of this. The sum of those two is our relative velocity that we observe in the rotating frame, VREL. And that multiplied by cross product of that with our omega, omega meaning this omega, because that is what we are rotating with, will give us the Coriolis component of the acceleration. So the idea is, first you look at a question, see how it is constructed. Look at the first rotating member over which other rotating members are mounted. You sit on the first rotating member. Now you are in a rotating frame of reference with some omega you yourself have. Now you are looking at perceiving things relative to you, which will be AREL and VREL. You just need to account for all the motions that you will perceive. Then appropriately apply the equations, it should be straightforward. Only thing that becomes a little more involved is that the cross products are three-dimensional, so you need to go by the determinant mnemonic. Other than that, there is nothing very different here. So for example, in this question, First, this is mounted, and then we have been told that this crane is spinning about the vertical with this. So you will sit on the crane first, and then you are spinning with the crane. Now you are already in the rotating frame. Then you observe relative to you, this boom is moving up or down. It is having angular motion. So like that, we have to build up the case and solve. So I hope that is clear. I'm sorry I've run out of time. I've extended the time by 20 minutes. I'm sorry to have extended it, but I had to cover all the fundamental problems. That is why it took a little time. Other than that, if there are any questions now, I'm happy to take them. So this happens to be the last session today, uh, and we will be closing it here. So this just serves as a recap. Other than that, I'll be posting this video along with the other videos. You can always refer them. And should you have any questions, you're always welcome to reach out to us in the forum. With this, I'll close this session and formally conclude this course. So I hope that this was of some substance and value to you. So we'll see possibly next semester some other course we'll meet. So with that, I'll close this session. I thank you for attending.